In the silent depths of space, a celestial giant churns, sending out whispers of energy across millions of miles. Our sun, giver of life, also holds the potential for unimaginable chaos. What if one of its most violent outbursts were aimed directly at us? An event so powerful it could plunge entire continents into darkness, unraveling the very fabric of modern society. A modern Carrington event. What would it look like? How would daily life transform in an instant? The questions linger, unsettling and profound. Our sun is a dynamic star, a churning inferno of plasma and magnetic fields. Most days, its activity is benign, providing the light and warmth essential for life. But beneath its tranquil facade, immense forces are constantly at play, building pressure, twisting, and snapping. These forces, when unleashed, manifest as spectacular phenomena, visible even from Earth. They are the initial spark in a chain reaction that could cascade across our planet, threatening the technological systems we rely upon. The year was 1859. Telegraph systems across the globe suddenly sputtered to life, delivering shocks to operators and even igniting telegraph papers. Auroras, usually confined to polar regions, danced vividly in skies as far south as the Caribbean. This was the Carrington Event, the most powerful solar storm in recorded history. A time when technology was nascent, and the world was largely unburdened by reliance on electricity. But what if such an event were to strike today, in our hyper-connected, digital age? The implications are vastly different. It begins with a solar flare. These colossal explosions on the sun's surface are caused by the sudden release of magnetic energy. Imagine twisting a rubber band until it snaps. On the sun, this energy release generates intense bursts of X-rays and high-energy particles, traveling at the speed of light. They can reach Earth in just 8 minutes, capable of disrupting radio communications and satellite signals. A dangerous precursor, yes, but often just the beginning of a much larger, more ominous threat from the heart of our star. But the true danger often follows, a coronal mass ejection, or CME. This is a massive cloud of magnetized plasma and solar radiation, hurled into space at incredible speeds, sometimes millions of miles per hour. Not every flare produces a CME, and not every CME is aimed at Earth. But when one is, and it's particularly powerful, it becomes a space weather bullet, traveling through the void with our planet in its crosshairs. A cosmic collision, delayed, yet inevitable, if its trajectory aligns. Thankfully, Earth possesses its own defense system, a powerful magnetic field, the magnetosphere, generated by our planet's molten iron core. This invisible shield largely deflects the constant barrage of solar wind and most smaller CMEs. When a CME strikes, it compresses the magnetosphere, causing it to ripple and reverberate. This interaction, though largely protective, can also generate its own dangerous effects, sending energy waves racing towards the Earth's surface, seeking out vulnerabilities in our infrastructure. When a powerful CME slams into the magnetosphere, it triggers a geomagnetic storm. The energy from this cosmic collision creates intense, fluctuating electric currents within Earth's upper atmosphere. These currents, in turn, induce secondary currents on the ground, geomagnetically induced currents, or GICs. It's these GICs that pose the most significant threat to our technological world. Invisible, silent, yet devastating, they seek out long conductors, turning them into unwitting antennas for destruction. America's power grid is a vast, interconnected network, a marvel of engineering built over decades. But its very design makes it vulnerable to GICs. Long transmission lines act like giant antennas, absorbing these induced currents. They then flow into high-voltage transformers, the heart of the grid. These transformers are designed for alternating current. The direct current nature of GICs causes them to overheat, distorting their magnetic fields. What happens when these crucial components begin to fail, one by one? A domino effect. A systemic collapse. Imagine waking up to silence. No alarm clock. No coffee maker. The lights remain stubbornly off. Your phone, a dead rectangle in your hand, unable to connect. This is the immediate aftermath of a widespread grid collapse. The modern world, so dependent on electricity, would simply cease to function. Cities, once vibrant hubs, would become monuments to darkness. The illusion of constant connectivity and convenience shattered. What would become of our digital lives? Our very identities, perhaps, residing in servers now dormant. The initial blackout is only the beginning. Without power, water purification systems would fail, leading to widespread shortages of safe drinking water. Fuel pumps wouldn't operate, paralyzing transportation. Supply chains, the intricate web that feeds our cities, would snap. Hospitals, unable to sustain life support, would face unimaginable choices. The economy, too, would grind to a halt. Experts warn that recovery from such an event could take months, even years. A return to normalcy, not a switch, but a grueling uphill climb. Our digital infrastructure, the very backbone of modern society, is equally vulnerable. Satellites, crucial for GPS navigation, weather forecasting, and global communications, are directly exposed to solar radiation. A powerful solar storm could knock them offline, damage their electronics, or even send them tumbling out of orbit. The Internet, reliant on a complex web of fiber optic cables and data centers, would struggle. Without power, without satellites, without the Internet, we would face a digital dark age, isolating us from each other and the world. To prepare for such an event, we must first predict it. Scientists constantly monitor the sun, using a fleet of advanced spacecraft and ground-based observatories. Missions like NASA's Solar Dynamics Observatory, SDO, and the joint NASA/ESA Solar and Heliospheric Observatory, SOHO, provide a continuous stream of data, capturing stunning images and measurements of solar activity. These watchful eyes are our first line of defense, scanning for the telltale signs of an impending eruption. They are our early warning system, however imperfect. Predicting space weather is a complex, formidable challenge. While we can detect flares and CMEs as they happen, forecasting their trajectory and intensity remains difficult. Unlike terrestrial weather, which develops over hours or days, space weather can change in minutes. NOAA's Space Weather Prediction Center, SWPC, plays a critical role, analyzing data from spacecraft to issue alerts and warnings. These warnings, though crucial, offer limited lead time. Often, we might have only a few hours, or perhaps a day, before impact. Is that enough? So, what can be done to protect our vulnerable power grid? Solutions involve both immediate operational responses and long-term infrastructure hardening. Utilities can implement protocols to reduce the grid's exposure during a geomagnetic storm, such as temporarily disconnecting transformers or rerouting power. But these measures are often insufficient for a Carrington-level event. The true defense lies in making the grid inherently more resilient, a monumental task that requires significant investment and coordinated effort. A key strategy involves hardening the critical high-voltage transformers. These massive, custom-built units are incredibly expensive and difficult to replace, often with lead times of over a year. Research is ongoing into designing GIC-resistant transformers, or installing devices that block or mitigate induced currents. Some utilities are also investing in strategic spares, pre-positioning replacement transformers in secure locations. But the sheer scale of the American grid means retrofitting or replacing every vulnerable component is an immense undertaking, a race against time. The threat of space weather is global, transcending borders. International cooperation is therefore vital. Countries share data from their observatories, collaborate on research, and coordinate preparedness strategies. Organizations like the World Meteorological Organization, WMO, facilitate these efforts, recognizing that a major solar storm impacting one nation could have ripple effects worldwide. This shared vulnerability fosters a collective drive to understand, predict, and mitigate the risks, uniting scientists and policymakers across continents. The sun's fury knows no boundaries. Beyond infrastructure, individual and community preparedness also plays a crucial role. Governments advise citizens to have emergency kits ready, with supplies of food, water, and essential medicines for at least a week. Local communities are encouraged to develop resilience plans, identifying critical resources and communication strategies that don't rely on the grid. While these measures can't prevent a storm, they can significantly reduce its human toll. The ability to endure the immediate aftermath could be the difference between chaos and recovery. So, could America's power grid survive a massive solar storm? The honest answer remains uncertain. While awareness has grown since the 1859 Carrington Event, and significant efforts are underway, the scale of the threat and the sheer complexity of our interconnected infrastructure present formidable challenges. We have eyes on the sun, brilliant scientists, and developing technologies. But the question persists, are we doing enough, fast enough? The sun, in its majestic indifference, continues its cycle, and with each rotation, the possibility of the next great storm draws closer. A silent countdown.